The other day in class, we talked about recipes. We made things I called s'mores. 2 marshmallows, 2 chocolate chips, 1 cookie made an animal cracker s'more. It was easy for you to see how to use the recipe to figure out how many s'mores you could get if, for instance, you had 30 marshmallows. If the ratio was 2 marshmallows per s'more, you could get 15 s'mores from your 30 marshmallows. That's pretty easy. And what we're going to learn in this chapter, called stoichiometry, the real thing, measuring elements, isn't much harder. It's just using chemicals instead of tasty things like marshmallows and cookies and chocolate. To make the problems easier to figure out, we're going to use something that I call the mole map. Every problem you do will involve going from moles of one substance, substance A, to moles of another substance, substance B. The thing that links them, and the conversion factor that you use to do that, is the coefficient ratio. And we call going from substance A to substance B, I call this connection the mole-mole bridge. The coefficient ratio is obtained from the coefficients in the balanced chemical equation. These are the large numbers in front of each substance that show the relative quantities of each needed to balance the equation. We can use the coefficient ratio to link any of the substances in a chemical reaction. We can go from reactants to products, or products to reactants, or any possible combination. Now, every problem you do will involve crossing this mole-mole bridge, but most problems will also involve doing other mole conversions that we learned earlier in the year. We can't measure moles directly in the laboratory, but we can measure mass in grams, and we can measure volume in liters. We can also talk about the number of particles, which is kind of what brings all these ideas together in the mole. So let's see how these things are linked, and this is kind of review. The mass of a substance, 1 mole of a substance, is its molar mass, and this is obtained from the periodic table. Either what's on the periodic table for an element, or the sum of all the elements and atoms that make up a compound from the periodic table. So grams per mole is one conversion factor we will use. If we're talking about particles, the conversion factor will be 6.022 times 10 to the 23rd particles per mole. Those particles can be ions, or atoms, or molecules, or formula units. If we're talking about volume, the units we will most often use are liters. And this only applies if we're talking about a gas at STP, standard temperature and pressure, which is 0 degrees centigrade and 1 atmosphere. 22.4 liters of a gas equals 1 mole of the gas at STP. Now, that is how we would, let me back up a minute. If you are given mass or particles or volume of substance A, you do a factor label problem to get you to moles of substance A. You would divide by the molar mass, divide by Avogadro's number, or divide by 22.4 liters per mole in order to get to moles of substance A. Then you have to get to moles of substance B. That's where you use the coefficient ratio. Most problems will not stop with moles of substance B, but will ask you to calculate on the other side, again, either mass in grams, using the molar mass as a conversion factor, or the number of particles using Avogadro's number as a conversion factor, or using volume using 22.4 liters as the conversion factor. In this case, on this side of the mole map, you'll be multiplying by those numbers. So, if you follow this map, you can solve any of the problems we'll do in this chapter. All of them will involve the mole A to mole B conversion using the coefficient ratio. If you are given grams to start out with for mass, you must first convert to moles. From moles of A to moles of B, you'll use the coefficient ratio, and if you're asked to give the answer in grams of B, you'll use the molar mass of B to convert from moles of B to grams of B. You might be asked to convert from particles to particles, using Avogadro's number to get you to moles of A, coefficient ratio to moles of B, and then Avogadro's number to particles of B. You might be asked to convert from volume to volume, following this path. First dividing by 22.4, then using the coefficient ratio, then multiplying by 22.4. Notice that with the last two examples, particles to particles and volume to volume, you are first dividing by a conversion factor, then multiplying by it. So it cancels out. So effectively, as you get better at these, you can see that you can go directly to the coefficient ratio to solve those. We'll see examples of those. Don't worry about that right now. You won't always be converting from the same thing. For instance, you won't always be going mass to mass, particles, particles, volume to volume. For instance, you might start off with volume of substance A and have to calculate for mass of substance B. Just follow a different path through the map. Again, always crossing through the mole-mole bridge. You might be asked to solve from mass of substance A to volume of substance B. And again, you can follow any way through this path. It just has to pass through the mole-mole bridge. And that's the important part to really master today with this. On this particular screen, what I'm doing is just very quickly jotting down the mole map. You should pause at this point and see if you can do this. It's not that hard. Start with moles of A to moles of B in the middle, and remind yourself that the coefficient ratio is the conversion factor. Then, off to the left, think about substance A. You might start with mass, particles, or volume, and jot that down, and remind yourself of what the conversion factors are. Then do the same thing on the right. Mass, particles, volume. You may be asked to go from any of these in substance A, mass, particles, or volume, through the mole-mole bridge to any of those features for substance B, mass, particles, or volume. But you will always cross the mole-mole bridge. It's very important that you understand that. Let's work through some very easy problems just to kind of demonstrate the use of this. Here's a word equation. Liquid water decomposes to form hydrogen gas and oxygen gas. First, we have to write a balanced equation. You should know that one. And from this, we see a coefficient ratio. You don't always have to write this down. I'm just pointing it out by writing it there. 2 waters react to form 2 moles of hydrogen and 1 mole of oxygen gas. Here's our problem. How many grams of oxygen come from 36 grams of water? So where do we start? We are given 36 grams of water. That's the known. We have to solve for grams of oxygen. Here's the way we'll go through the map. Grams of substance A, grams of water to moles of substance A. Across the bridge to moles of substance B, oxygen, to grams of substance B. And I'm just going to use whole numbers here for my masses just to keep the screen from getting cluttered. I still want you to use molar masses to the hundredths place and round appropriately for sig digs. So first we go from grams of water to moles of water, canceling out using the molar mass. From moles of water to moles of oxygen, using the coefficient ratio, 2 waters to 1 oxygen. From moles of oxygen to grams of oxygen, using the molar mass of the oxygen molecule. Do the math and you get 32 grams of oxygen. Let's solve it for something different. How many liters of oxygen can we get from that 36 grams of water? Here's how we'll follow the map for this. Grams of water to moles of water, to moles of oxygen, to liters of oxygen. Same setup to start off with. Moles of water to moles of oxygen. But now we're going to use a different conversion factor. Instead of grams of oxygen, we want liters. There you go. Let's do one more. How many molecules of oxygen from 36 grams of water? The way we'll work our way through the map is grams of water to moles of water, to moles of oxygen, to number of molecules of oxygen. 32 grams of water is 2 moles of water. This is the same. Coefficient ratio, 2 moles of water to 1 mole of oxygen. Again, you're using factor label to do this. And finally, we need to figure out the number of molecules by using Avogadro's number. 6.022 times 10 to the 23rd molecules of oxygen. Once you get the hang of it, they're all pretty much the same. And I think that's about it for now. Thank you.